All right, so welcome everyone to Map Time Davis. I'm really glad that you all are here. My name is Michelle Tobias. I'm the Geospatial Data Specialist at UC Davis Data Lab. And today we are going to have a workshop on spatial stats in R with my colleague Wesley Brooks, who also works at Data Lab as a data scientist. Before we get into the workshop materials, I want to go through some quick announcements about what's going on with Map Time. So I'll post some links to the things I'm talking about in a moment. But I want to make you aware that later this quarter, so we've got 2 more workshops coming up, or 2 more, I guess let's call them sessions for this quarter. So next week, I will be hosting a Map Time Davis studio discussion about art software for cartography and other visual research communications. That's a big title, but basically what's going to happen is folks who are interested, I'll show sort of my workflow and how I work with art software. In particular, I work with Inkscape, but it's kind of a similar tool to Adobe Illustrator. The concepts are the same, the programs are quite different, as you might imagine. So if you have questions about how to finish up maps and make them look really super polished, or how to polish up things like graphs and or diagrams and things like that, next week, May 11th, we'll be having a session for that. So please come to that. And then the last session of the quarter and the school year is going to be lightning talks. Evelyn Pless is organizing that. If you're interested in presenting about your research in a quick talk format, should be a really good session. It should be really fun. Whenever we have lightning talks, I always learn a lot from everybody's presentation. So I believe we're still accepting people to join up with that. So again, once I finish this, I'll post a couple links for you to follow up with seeing the whole schedule and all that. The other cool thing we have going on right now is this week is the last week to submit applications to join Map Time Davis Council. And that is a new advisory board and volunteer organization around Map Time and the Spatial Sciences Research Cluster at Data Lab. We need more participation at sort of an organizing level. And we've got some really good applications, but I'd like to see a couple more. In particular, it'd be really good if we can get some folks who have more experience in the remote sensing field and also in the programming languages and things like that. But people with experience in any range of geospatial are certainly welcome. So I'll put the link in the chat soon for that. But I believe we set the due date for that on Friday. So, and I won't be extending it. We've got plenty of applications, but if folks would like to apply, that is still open, and I would definitely encourage you to submit your application. That being said, the application is not intended for you to take a long time. It's not supposed to be a huge deal. So, you know, don't spend a ton of time thinking too hard about it. It's not intended to be a giant essay type thing. It's kind of quick answers. So, so basically, I just encourage you to apply. I think it's going to be a good group for next year. And yeah, so again, I'll post the links for all of this as soon as I stop talking, because I can't multitask. All right, so that being said, those are the 2 things I need you to know about: the schedule and also the Map Time Davis Council applications being due this Friday. So with that, I'm going to turn it over to Wesley to start our workshop today on spatial stats. So take it away, Wes.
All right, thank you, Michelle. It's really cool to be here talking with you all. This is a topic that I find really fun and totally confusing, as well as fascinating, you know, no matter how much studying I do. And I'm sure that some of you are probably in that same boat. So to get started, I want to make sure that we're all going to be on the same page. So I'm going to put a link into the chat, which is the link to a course reader that I'm going to be following for this workshop today. And I'm also going to start sharing my screen and show you that reader on my computer, so you can see what I'm talking about. There we go. Okay, so we're looking here at the front page of the reader, and the address that I posted into chat is up here. So if you follow that link, you should get here. What I'm going to be doing today is running through R code. Like, this is an introduction to spatial statistics in R. And spatial statistics is a huge subfield and a relatively small number of practitioners. So it's this sort of Wild West feel to spatial statistics. And it can get really confusing with a lot of jargon and a lot of very closely related methods that have different names. So I'm going to be following one particular path, and deviating from that path is liable to get, like, if people run into problems or aren't following specifically what I'm doing, there's likely to be issues, just because that's always the way it goes. So I'm going to try and go slowly and make sure that everyone can follow along. I'm going to be working in RStudio and in R. So as Michelle mentioned, if you don't have R and RStudio installed, this would be your last chance to do so if you want to follow along. The place to go to get that would be r-project.org. And there is a downloads page, and you can scroll down to find USA and follow that to whatever download is appropriate for your computer. There is a functionality within Zoom that allows me to wait for people it allows for you to put up a block saying like, oh no, I'm not ready to proceed yet. So if you are hoping to follow along and you don't currently have R installed, I will give you some time to do that, with the warning that this process will go more smoothly for people who have a bit of practice with R, which I know is at least a portion of you. Okay, so I'm going to stop sharing this screen and show you the environment that I'm going to be working in as we go through the workshop, and that hopefully, well, if in an ideal world, will basically mimic your environment. This is my RStudio. I have open this document here, which I've called code along, but it is empty. I'm going to be typing R code into this script, running it in my console. We're going to see output here in the console. We're going to see plots in this panel. We're going to see variables as I load them appear in this environment panel. So this RStudio window is going to contain everything that, like, if you're following along as I go through, you will be doing the stuff that is in the course reader that I'm doing here in this window, and hopefully being able to check your results against the things that you see both in the course reader or the workshop reader and in my interactive environment. So there are people in the chat who can respond to questions. Like, that's going to be Michelle for some stuff and other R users for other stuff. Like there might be things that only I can answer, but I think that for the most part, we're going to be able to help each other out and keep up. And I'm going to go at a pace that hopefully everybody is comfortable with following. So I hope that's clear. And I'm also just taking a moment here to let people who are getting caught up or have not gotten to the workshop reader to get there and get started, as well as get started up in a fresh new RStudio environment. You can see that the first package I'm going to be using here is called random fields. One thing that I realize I haven't done is included the install. So if you're new to R, you might not understand how to install packages. So this is a great place to start. If you are a new R user, you definitely would not have the random fields package installed. So the way you would install that is to go to your console and type install.packages. And then in parentheses, in quotation marks, random fields, same capitalization as I have in the import call. And I assume we are all connected to the internet because we are here on a Zoom call. So you should, if you did not already have that package installed, you would reach out to the internet, download it, and then you would be able to import it when I get to. The import of the package is what's happening here with this call to a function called library. I haven't combined all of my library imports into one block, so there will be future blocks where I import packages. And I'm going to go slowly through those because, again, we'll probably encounter some packages that people have not yet installed. But if you want to get started on that, we're definitely going to be using a package called SF. So library, or sorry, yeah, you would install .packages SF. That's an important one that, again, it might take a few minutes to install. So I would encourage people to get started by following along with that. Okay, so hopefully that's enough time to get everybody caught up, and I'm going to flip back to my web browser for a moment because I wanted to point out that if you are getting, if this is something like your first exposure to doing spatial statistics, one resource that our users might have seen, might not have seen, but might want to get familiar with is the CRAN spatial task view. CRAN being the comprehensive R archive network. It's the official repository for all R software. So if we click their spatial task view, we're going to see this, which is ugly. There is just such a diverse amount of packages for spatial data analysis and visualization and manipulation and import. And so many of these packages do really similar things, but they have completely different vocabulary, or they don't obey the same, or like they don't have the same arguments to their functions. It gets really confusing, really annoying. And even for somebody who's spent years, working with spatial data and studying spatial statistics, I still, I see this and my head starts spinning. It's crazy. There's just so many different packages and they just are not well unified around a particular format of, specifying data. So one of my key goals in this workshop is to provide for you some guidance as to how to do the basic first steps, because there's no way that you're going to learn comprehensively how to do spatial statistics in one workshop. So this is definitely an introduction and first steps. And one really critical thing I'm hoping to help with is pointing out what are some of the best packages among the ones that are available for R, so that you don't see this R task view spatial and get totally confused and upset and decide it's not worth trying to learn. So I'm going to be trying to focus on the most relevant and comprehensive and up-to-date and popular packages, so that hopefully what you learn stays relevant for a long time. And as hopefully these packages continue to grow and develop, they will coalesce to a sort of singular vocabulary, which is not totally the case yet, but there has been some improvement in that environment, in that direction. Okay, so this is, like I say, the spatial task view, and reading it can be kind of interesting to get an idea of what spatial statistics is all about. But
Hey Wes, can I interrupt for just a second and say that the font on the screen for everything you've been showing is really small. If you could make the font bigger here, and then also in the R console, that'd be a little bit easier for us who are trying to follow along on the screen.
Thank you. That's
great, thanks.
A great reminder. Okay, so I am going to get started talking about the types of spatial data that we're going to be discussing today. I'm going to flip the screen share back to my RStudio. Whoops, wrong RStudio. There we go. Okay. So, spatial data. There are three basic kinds of spatial data that are most important, and I'm going to try to give a brief introduction of all three of them today. We'll see how that goes. But I break this out into geostatistical data, which are measurements of some continuous field, but are located at a specific point. So you might imagine something like air pressure or temperature, that those numbers exist everywhere, but when you observe them, you're observing the value at a single point in space. I'd also like to talk a bit about aerial data, where observations correspond to an area. So that could be a county or a raster cell. And these might be things like, when we compile or combine all the votes for a state, you see the maps that like color each state by how its presidential vote turned out. That's aerial data. It's combining it's aggregating or summarizing some value at the level of an area as opposed to a specific point. And then point data are a unique kind of data that arise from observing an area to see where and how often some event will occur. So things like where do plants grow are a kind of point process data, or where did car crashes happen. The data, in that case, you're not going out to a specific location and making the measurement, but rather you're observing an area and noting the locations where something happened. Okay, so moving on, there is a unifying concept that lies behind all of these. So before we talk about the particular kinds of spatial data, I need to go on to my chapter 2 and talk about random fields. And in the course reader, because it is May the 4th, which is Star Wars Day, I found a nice Star Wars quote that sort of summarizes what I'm talking about with random fields, or at least is a nice metaphor to my mind, which is Obi-Wan saying that the Force surrounds and penetrates us. It binds the galaxy together. So a random field is something like the Force in that way, in that it is everywhere without being seen. So I mentioned previously temperature and air pressure. You could have air particulate concentration, groundwater pressure, soil lead concentration. Like these phenomena are continuous in their domain. So they cover stretches of land, or well, they cover like areas or even volumes, but you can't observe them on that scale. When you take observations, the observations you're only realizing the value of this field at a particular location. Or if you're talking about, even if you're talking about an area, you're seldom actually measuring something that covers the area. You're maybe aggregating the votes in a state, or you're aggregating the incomes in a state, or the temperatures that were measured, but you're not actually able to observe everything. Public sentiment might be another thing that actually you could think of as being a field that exists everywhere. Like there's a gradient in political attitudes as you move from west to east across the country, or north to south. And while those attitudes are carried by individual human beings, like you can nevertheless, on the broader scale, see that there is some random field that, depending on where a person lives, they take on attitudes that arise in that location, right? So our data our data don't surround and penetrate us. They're not like the forest. Our data don't flow through everything. We have sparse measurements of this abstract thing that I'm calling a field. And so the task in spatial data analysis that makes it different from other kinds of data analysis is estimating the parameters of a random field. Okay, so in the course, or in the workshop reader, I've prepared a couple of figures to give hopefully some intuition about what a spatial random field looks like. So once again, I'm going to flip over to my web browser. Hopefully you're able to see this yourself. Now these are locations on Rongelap Atoll, which I'm going to talk about later. These are 157 locations where gamma ray monitors were put on the island. And the intuition I'm trying to illustrate here is that we have individual locations where observations were made. That's this Z1, or sorry, Z2, Z37, Z135, Z141. There are 157 of these locations, even though the radiation that's being measured covers the entire atoll. Then between any pair of locations where data is observed, we can measure the distance, the pairwise distance. So I've here in purple highlighted the distance between observations 141 and 135. And in orange, I've highlighted the distance between observations 2 and 37. And obviously that distance is quite large. This distance in purple is quite small. So you might expect the points 2 and 37 to be less closely related to each other than the points 141 and 135. Because as the distance grows between points, really frequently we're going to expect that the amount of correlation between those points, between the data at those points, becomes weaker. Okay, so scrolling down then to the second of these images, here's where this is the worst image in today's talk, and it involves the most math. So bear with me and we'll take our time. And don't worry too much about memorizing anything in particular from here. Again, I'm just trying to explain something about random fields and hopefully provide a bit of intuition that is going to help you as we move along. So in the first of these images, I said that there are 157 locations where gamma ray monitors were placed on the atoll. And so I have here on the left-hand side of the figure posted a vector that says, or that lists Z1, Z2, Z3, and all the way down to Z156 and Z157. Those are observable data, things that you can actually go out and measure. And there's only 157 of them, once again, even though the real life random field is this unobservable force, if you will, this unobservable field that covers all of the area of the atoll. Okay, well, these are observable data, but in order to be able to do statistics, we typically want to think about a population or a distribution of that data. Now, with spatial data, that always means when we're talking about a random field, we're talking about a normal distribution. And there's a very good reason for that, which is that there are very, very few multivariate distributions in the world. And the normal distribution is far and away the best understood and most studied of them. And it's for that reason that we rely on it for everything when it comes to describing spatial fields. So I'm going to spend a little bit of time explaining this multivariate normal distribution that I've posted here, because I'm guessing some of you don't have any background in statistics. And again, this is a cartoon version. You don't have to memorize any math. You don't have to really understand the details. I want to get the general idea across. Okay, so this n is just just an abbreviation of normal, meaning it's a normal distribution. And I've got this Greek letter mu here, and those are averages. That's the mean value of the random field. And in the simplest case, we just assume that mu is a constant. And you might even just assume that mu is equal to 0, or the average of the observed data values. So in the simple cases, mu can be almost ignored. And because it's the mean value, it also is the pattern that jumps out most readily when you look at the data. So I'm going to ignore mu for the moment, but you can think of mu as just being the average value that covers the entire island. But of course, these observations aren't average. There's going to be some amount of variability. And like I stated in the previous picture, we expect that correlation in that variability to be greater when observations are nearby and less when those observations are far apart, like 2 and 37. Okay, so we have this big 157 by 157 matrix called the covariance matrix of this of the distribution of these data points. And there is one point in this matrix for every combination of 2 points. So there is a point in this matrix for the covariance of Z2 and Z37. There is an entry in this matrix for the covariance between Z135 and 141. And then there along the diagonal are the entries for the variance, the individual variance of each data point. Okay. Now covariance just means it's a fancy way of saying that when one changes, the other will tend to change in the same direction. Or if covariance is negative, then you'd say when one data point changes, the other data point tends to change in the opposite direction. So that is capturing the relationship that is meaningful to us here, the spatial relationship. And I've written down a really simple sorry, I shouldn't say it's really simple because some of you might not consider it to be that way. But what I've written down below is the form of the exponential covariance function. And it might look complicated because it has a lot of Greek letters, but I want to explain it to you. And again, not in every detail, but just to try and get the gist so that you will help begin to develop the intuition. So I'm writing here the covariance between the measurements at Z2 and Z37. And if I scroll up here, you'll see again, these are these 2 observations that are separated by D237 and indicated by the orange arrows. So the covariance between those points ought to be relatively small. How do we assure that? We assure that by saying that the covariance is equal to, okay, some constant here, that's sigma squared. Let's ignore that constant because it's constant. We get to estimate that from the data, and because it's constant, it's not too difficult. So some constant, sigma squared, times the exponential of negative distance divided by rho. So to start with rho is called a range parameter, and it has to get estimated. But think of rho as just a range, and meaning that it is the distance at which the covariance between the points tends to get very small. The important part is that we have negative distance as the numerator in that exponent. So as distance becomes greater, this value in the exponential becomes more negative, and therefore the exponential itself evaluates as closer to 0. So you can see that if distance is quite small, this exponential could be close to 1. because distance is always positive. So negative distance is always negative. And as distance gets large, this exponential gets closer and closer to 0. So that is one form that helps capture this relationship of nearby observations being more similar than distant observations. And I'm now going to flip back to my RStudio, and hopefully you all should follow along both in RStudio and in the reader. And I'll show you the form of that, well, I will show you the form of that exponential covariance. Okay. So first thing I'm going to do is set my range parameter. And remember that I said range is a distance at which the relationship gets small. The covariance between 2 points gets small. I'm going to set it to 2. I'm going to say that I'm going to just set up some distances here, a sequence from 0 to 10 with a length dot out equals 200 or 300, I guess, to keep it in line with what I put in the reader. Okay, then I want to, actually write the covariance function. So I'm calling that cov_fun equals exponential of minus tt divided by range. And then I want to plot tt covariant cofun. I want to make this a line plot, and I'm going to label the x as distance. I'm going to label the y as correlation. Okay, so this is what I was describing. As the distance is close to 0, the correlation is close to 1. As the distance grows, the correlation tends to 0, but never exactly reaches it. There are other correlation functions that take slightly different shapes or even radically different shapes. And we're not going to concern ourselves with all of that. Know that there are plenty of options and you don't have to know them all. And that this one, the exponential correlation function, is extremely common. All right. Now, there's another way to look at that same plot, which is as something called a variogram. And to do that, I'm going to now create a nugget variance. And that nugget variance is the residual measurement error, see how to put it. It's the residual measurement error if you were to measure the same location multiple times. And that's because measurements are always made with error. So there's typically some small amount of variance that you could not eliminate, even if you measured the same thing multiple times. Whether that's because of the instrument's variability or the user's eyeball not being able to distinguish too clearly on a scale. It's just an amount of variability that is present even if you try to repeat the exact same measurement. Okay, that's it. I was going to plot the variogram version. So once again, that's the plot function. I'm going to plot TT. And this time, instead of just plotting covfun straight out, I plot 1 minus covfun. And I add the nugget variance. Okay, again, this is going to be a line plot. So type equals L. And again, the X label is distance. And the Y label is, this time we call it semi-variance, which is jargon. Don't worry about it. And that's right. This is not quite what I wanted to do, because you can see that the y-axis starts at 0.2. So I want to make sure that ylim equals 0 and 1.2. Okay. All right. So here is an extremely common semivariance that if you do any spatial statistics, you might see again and again when you plot variograms. Don't worry about the jargon. We're going to talk about variograms quite soon. The nugget is this gap. At distance equals 0, there is still variance. But as the distance grows, that semivariance gets larger and larger, meaning the relationship between observations gets weaker and weaker as the distance between them grows. Okay? So that should just help inform your intuition of how spatial statistics actually does make sense. And random fields, even though they're a little spooky, there's no reason to be afraid of them. They obey the sort of natural rules that you might intuitively understand about nearby things being more similar than far away things. It's just a way to formalize that relationship. Okay, so in order to make that a little bit more concrete, before I even get to data, I want to show you how to simulate some realizations from a random field. And the reason I like to do this is because if you actually want to study spatial statistics and try learning new techniques, being able to simulate data is a huge benefit, because when you simulate your own data, you know the truth, you know the true parameters that were used to make the data. And therefore, when you do your estimation, you hopefully are going to recover parameters very much like the real ones that you used in simulation. Another reason it's good to be able to know how to simulate data is that it provides a really quick way to work through examples with data, as opposed to having to seek out data sets and clean them and make sure they're in an appropriate format before you start work. So you can churn through a lot more practice with simulated data than you can with real data sets, because real data sets are a lot more work. Okay, so simulating some realizations of an exponential model, just so that I can be sure that you know what we're talking about. First, I'm going to define the covariance model. Oops. I almost put it in the console instead of in the code. Okay, so I need to define a covariance model. And here's where I need to have random fields installed. So again, if you don't have random fields loaded yet, then do so with library random fields. Then I can set the covariance model equals rm exp, and I'm just going to use default parameters, nothing fancy. Let's say that x is a sequence from 0 to 10. And it's going to be in 100 steps. And then I can use the, okay, z equals rf, so standing for random field simulate. And I specify, let's see, I specify the model and the x values. So the model is, I called it model. The x values are x. The y values are also x. It's just a way of defining a square. And then n equals 4. So n equals 4 simulates 4 realizations of this random field. And I want to do that. Oops. Invalid components, listing, parse lines. Okay, what did I do wrong? This is, I believe, the same as what I have in my code. Oh, warning message. Okay, then, sorry, I thought that was an error. In fact, it's only a warning, so I'm going to ignore it. Okay, and then I'm going to print those 4 random fields, which I called Z. Print, I meant to say plot. Okay, so these are 4 random fields that I have simulated. And once again, if you are getting started learning about doing spatial data analysis, being able to simulate data is a really great way to have new and untouched data sets in order to practice on. But you can see how these look. You can see there's clumpiness to these. Like this isn't like snowfall static on a television. There's clearly some areas of lighter yellow and darker red that are clustered together, and that is the spatial relationship. But they are completely random noise. It's just that that random noise has a spatial relationship. Okay. I already did plot the simulations. I want to then illustrate what happens if you choose a model other than the exponential model. So I'm going to choose RM cubic. So this is just doing the exact same thing, except with a different model for the correlation function, the covariance function. Whereas before I used an exponential covariance, now I will use a cubic covariance. But again, the simulation works the same way, RF simulate, specify the model as M2, again, use the same locations, and again, let's make 4 realizations. And I'm going to plot Z. Okay, these are my new realizations. You actually can sort of tell a difference, but you and I would both be hard pressed to know without being told which one you're looking at. And I like to illustrate that just so you know that the differences between all of these covariance functions can be quite subtle, and people can spend an awful lot of time thinking about which one is best and justifying choices like that, when in reality, the differences are small, perhaps not super important. And in my opinion, that's a fact that really contributes to the way that spatial data analysis has this huge diversity of methods that have been developed that don't really work together, because everyone is free to come up with a slightly different method that works equally well, and you can't really tell the difference between other people's methods, but it develops into this forking nightmare of 1,000 different choices to make to accomplish roughly the same thing, no matter which way you go. So that is our introduction to random fields.
I have a question in the chat for you, Wes. Naomi's asking if you can show the code again really quickly, what you just went over.
Yeah, I can. It's great. It's shown on screen now, but I would also point out that all of this is on that workshop reader, the website, which has the link in chat and that I've shown you a couple of times. I'm sure other people have that link as well. So everything I've just done is also in that reader. And speaking of the reader, at this point, we're moving on to the 3rd chapter in it, which is about geostatistics. And at the start of that section of the reader, I have listed the packages that are going to be used here. So I'm going to import those now myself. Maybe to make Naomi happy, I'll leave a little space here. Eliminate some white space so you can hopefully see a little more. Okay. So you may or may not have any of these packages installed already on your R. ggplot and reader are both part of the tidyverse, so a lot of people likely have those and are familiar with them. Just going to import them here. Gstat and stars are packages that are specifically for spatial data analysis. And so folks will probably need to install those now in order to follow along, because most people probably do not have those installed. But speaking of my earlier point about guiding you toward the best and most useful packages, Gstat is becoming a real standard for geostatistical data analysis. And remember that geostatistical data is the kind that is continuously existing everywhere as a field, or like the force. It moves through everything and it unites the galaxy. And yet, when you want to observe it, you can only observe it at a specific point in space, so at a specific location. So again, we're analogizing to say air temperature or like soil, soil lead concentration, some sort of pollution like that. So that's geostatistical type data. Gstat is a really good package that is becoming the standard for that. Stars here is a package that is it contains a specific data type that I have to use once. I'm not as thrilled about stars as I am about Gstat, but it is necessary for one of the things I want to do here. And I should also have put here SF. The SF library, Simple Features, is a really modern package for working with spatial data. A lot of you in map time have probably heard of SF, the R package, or just of SF, or just of Simple Features in general. But one of the nice things about Gstat is that it plays nice with Simple Features data. So that's one of the things that makes it modern and useful as compared to a lot of the other packages you would find on the CRAN spatial task. Okay, so I'm going to go through and import Gstat, stars, and SF. I hope that people have had a chance to install those if they weren't already installed. And because this is geostatistical data, I got a geostatistical example for you all. And the first one that I'm going to show you is a repeat of what we saw before, that atoll. That is Rongelap Atoll. It is in the Marshall Islands, and it was irradiated by a US atomic test in 1954 when one of the first hydrogen bombs accidentally or due to neglect had a much greater explosive power than calculated, and it caused a lot of pollution. It made a lot of Marshallese and like some Japanese fishermen very sick, and made some people's homes uninhabitable for generations. So one of the things that's been done is on Rongelap, which was downwind of the test, which happened at Bikini Atoll, the US government put in a bunch of gamma ray detectors to measure radioactivity on the atoll. And that is the data that I'm going to load here. Now I have here, ordinarily I'm going to be typing at a speed you can follow along, but this particular command I would advise you to copy out of the reader and just paste into your RStudio, because it involves this really ugly URL that I don't want to type, but I don't think you want to type either. But the reason I provide the data as that URL as opposed to a file to download is that now you don't have to download the file. You don't have to worry about what path you're working in versus what path the data is stored in. We're just going to load this directly from the internet without any breaks in between. So that makes life nice and easy. Okay, but that was a CSV, so we can view Rongelap. So this is just a typical data frame. Okay. Columns of data, rows of data. We want to convert this to an SF object so that we get some of the features that come with simple features like calculating distances and the like. So I'm going to convert Rongelap using the st as sf Rongelap. Chords equals, these columns are called x and y. And we don't have a coordinate reference system because I don't know which one it was encoded in. Doesn't matter for our purposes now. Okay. Now, having converted the point data to SF files, I'm now going to once again copy out of the reader and paste into my RStudio the command to import the outline of the island. And once again, it's loading it directly from our GitHub repository. So there's no need to download anything. That's all handled automatically. So I once again would advise you to go and copy that file directly out of the workshop reader and paste it into your RStudio. And then I run it and I have loaded in Rongelap _ shp, which is a shape file. Okay. And yes, before I even plot those, what I wanted to do was show a histogram of the gamma ray counts so that I can justify using a log transform. So hist Rongelap val. So you can see that these data have a long right tail. They are all positive. The peak that's quite low, but then some very large counts that tail off. That's typically a sign that we want to do a log transform. So let's look at what happens if we do a log transform. So I say with hist of log of val. Okay, so this looks more like a normal distribution, which is nice because that makes our estimates a bit more reliable. We have a peak with tails tailing off on either side. That's what you like to see. Okay. Now I'm going to plot the data, and I'm going to use a two-way gradient to exaggerate differences, because otherwise the differences can seem kind of muted. So I'm going to use ggplot to plot the data. So hopefully you have imported ggplot2 or loaded that package. So start by plotting the shapefile of the outline of the island, adding the geom _ sf to make that a SF plot. And then I want to add another geom _ sf to plot the actual points. And these ones, I need to specify a mapping. And that mapping is AES color equals log of val. So what I'm telling ggplot here is that the color of the points where observations were made should be coded according to the log of the gamma ray count. Right. Then I had a couple more items I wanted to add in the command here. Oh yes, I want to do the specify the colors. So I need to add a color scale color _ gradient 2. That's a two-sided gradient, which means that the middle values will be colored, low radiation will be colored blue, middling radiation will be colored white, high radiation will be colored red. Of course, it's all high radiation. This is all, I'm just talking relative to other measurements on the atoll. Okay, limits equals C. Midpoint equals 7.5. So this is a complicated thing, but oh, and just to make it look a little nicer, I'm going to add theme underscore BW. So this is a complicated command, but breaking it into pieces, we begin by making a plot of the outline of the island. Give it a simple features geometry. Then we add another simple features geometry for the actual points that are colored by the log of the value with this particular color scale. So the individual pieces are relatively simple to comprehend, but altogether it's kind of ugly. But the benefit is that we get this fairly nice looking graph. And you can see once again that there is clustering of the data. Like you can see the highest radioactivity is here at the northwest end or northeast end of the atoll. The lowest radioactivity is here at the southwest end of the atoll. And there doesn't appear to be anywhere where you sharply go from quite high to quite low radioactivity. So that's an indication that there is some spatial relationship in the data. Okay, so that is all, importing, plotting, investigating the data, but we haven't actually done any statistics on it or analysis. So what do I want to do? I want to do Kriegging. And Kriegging is a pretty fundamental approach in a geostatistical analysis. And I'm going to do a very simple example of Kriegging. So don't be scared off. You may have been exposed to Kriegging in software like QGIS or ArcGIS. And it can get very complicated, but today here, I'm going to keep it simple. So let's all proceed. Kriegging is a form of spatial prediction where you specify a new location within your spatial domain. So I can specify any location on the island and say, I want to predict what the gamma ray counts at this particular location would be. And Kriegging works by essentially averaging the nearby locations based on how far away from that prediction point they are. So first thing I need to do is have some prediction points, and I'm going to generate them by holding out some observations from the Rongelap dataset. And the reason I want to do that is because by holding out some data at this point, I can then use Kriegging to predict what those values are. And then I have a predicted and an actual value, and I can make a comparison of them. So it's nice to do this with held out data. And the way I'm going to hold out data is by specifying, like taking 30 random points off of here. So I'm going to sample from 1 to the number of points. Then I'm going to specify one data set, which I call R2, which is where I remove those sampled values. So this is the one where I'm going to remove some data points from the set to estimate with. And I'm going to then make another data set called R3, which is containing only those data points indicated by index. Okay, so R2 is the data with these 30 points removed. R3 is only those 30 data points. Right, so I've held out some data to use later as for prediction. Now, here's where I actually do the Kriegging. Rongelap underscore fit equals. Okay, I use the Krieg function. This is from Gstat. So yeah, you can see here that my context menu pops up and says like I have this function from Gstat called Krieg. That's what I'm using to do Kriegging. I need to specify what is the Kriegging model. Well, for me, it is log of value as a function of just constant and intercept, right? So what this means, if you've ever used R before, if you've made like linear models, for instance, you might be familiar with this tilde format, where you specify a variable on the left, which is your response variable, and then a variable on the right, which are your predictors, or some set of variables on the right, which can be predictors. And you might or might not know, because this is not super common, that if you only specify a 1 over here on the right-hand side of the tilde, then what you're doing is estimating a model where there is only an intercept, or rather only a mean, right? And remember, when I was telling you about random fields, I said that the mu part, the mean part, so not the variation, but the average value, can be as simple as just a constant value. And that's what I'm doing here. Okay, so I also need to specify that R2 is the data to fit from, R3 are the points to predict to, and here is the most complicated part. I need to specify that model equals VGM, which means variogram. And I'm just going to specify a particular one here. It's going to be an exponential model. So we looked at exponential random fields. You've seen some simulated ones. Now I'm going to use one in a real setting. And I need to specify the range. So this is 500 meters is the range parameter, and 0.05 is the nugget. Which, yeah, okay. So now I can fit the model, and you can see success down here, no error messages using ordinary Kriegging. Looks like everything went. Great, so now I can plot the result. And what I'm going to do is plot only the predicted values. So once again, going to create the complicated ggplot. I'm going to go through it a little faster this time because I already went through it point by point here. ggplot, draw the outline of the island. Then I want another SF geometry using the Wongelap fit. And use the variable one dot var, or excuse me. This is data equals. And I would want to put so specify the mapping to be that color equals var1 dot var. And I'm going to use the same color scale again. So this is scale color gradient 2 with midpoint equals 7.5. Range is 4 to 10. The low color is blue. The high color is red. Oh, this shouldn't be called range, it should be called limits. All right, so I clearly got something wrong with specifying the color. Oh, var1.pred. Excuse me. All right, so these are the predictions for those held out data. And you can see that at least at a cursory glance, they seem to follow a comparable pattern to what we observed with the actual data. That is greater gamma ray counts toward the northeast, and especially in this little curve of the island, and then the lowest counts present down here at the extreme southwest of the island. So we can actually compare the predicted values that we've just generated using this Kriegging model to the actual values and see whether we got anywhere near the right trend. So I must have hit caps lock, so I'm going to plot. Wrong with that. All right, so these will be the predicted values on the x-axis, and then on the y-axis we will have our $3 $val, which are the actual values. Okay. Oh, I forgot to log data. Okay, that looks better. And then I can draw a one-to-one line here to see, like, if the model were perfect, data should fall, these data should fall on an exact line, which obviously they don't, but there is a trend here. And let's see how close that trend is to the line. Okay, well, that line is about where you would draw it by eye. So there's definitely some variability, some uncertainty to the predictions. They're not perfect, but we are capturing something like an accurate trend, which is good. Okay, so sticking with geostatistics, I wanted to move on to a slightly more complicated model. And in order to do that, I'm going to import some new data. And this time it's data from the Meuse River in northern France. And this is data on soil pollution, and we're going, particularly heavy metal pollution in the plain of the Meuse River. And we're going to focus on zinc pollution. And the reason I want to do another example is, one, to expose you to a little more, to another example, give you some reps. But I also now want to make a slightly more complicated Kriegging model, one that is not just a constant mean value, but actually has a predicted trend for the mean value, as well as not simply specifying the variogram to use for Kriegging, but rather to estimate it. So now we're getting closer to something that you would do with data. But once again, we're going to focus on the same thing, which is we've got a bunch of observations, and how do we use those observations to make predictions at different locations. Okay, so loading the Meuse data. I'm once again going to copy this line directly from the workshop reader because it involves a download from the GitHub page, and I don't want to type that URL. And now I'm going to convert that CSV that I just imported to an SF type, a simple features data. Okay, and the chords in this case are again called XY. And again, I want to show you that here we do want to do a log transform because the zinc concentrations are also, they also exhibit a long right tail. And just to show you that, these once again, like all the data are positive, and it's a peak near zero with a long right tail. So we typically handle data like that by a log transform. If we do a log transform, we'll see that the data begin to look much more like a normal distribution, which so again, now a bulge in the middle, tailing off to both sides. That's going to generate more reliable predictions, especially when it comes to inferences about the variability of our predictions. Okay, but we've already seen that, so I don't want to belabor it. What I want to do is jump into new stuff. So here I'm going to make a plot. It's a bubble plot. It will show all of the data observations, observation locations with a bubble sized to the zinc concentration. And the reason I do that is because the locations will show us how dense or sparse the data are. And then the size is a really convenient way to display the quantity of something, in this case, the quantity of zinc pollution. Okay, so I'm going to use ggplot again. And the data here are Meuse plus geom_sf. Right. I have mapping. Right size equals zinc. And let's say color equals green. And alpha, which is a transparency parameter, equals, what did I put? 0.6. Okay, so this is a map of a plane of the Meuse River. The river flows, or you can see that this is a big bend in the river. It's to the bottom left of this window, the river's making a like sweeping curve and then running straight toward the upper right of the image. And most of the data observations are clustered around the river. And what's more, the data observations that are farther from the river have the smaller dots indicating a lower zinc concentration. So less pollution the farther you get from the river appears to be what we are seeing from the data. Okay. Well, that is the relationship that I want to incorporate in the I want to incorporate that relationship of less pollution, less zinc pollution as you get further from the river as the fixed trend or the mean trend in my Kriegging model, as well as estimating the variogram to explain the remaining variability, or at least to model the remaining variability. Okay, so there's some jargon in there, and I think actually showing the example is going to help resolve that or make it a little more comprehensible. So I create a new variable called vario, and it is a variogram, and it is log of zinc is the response. Function of, and I'm going to use the square root of distance because I happen to have already looked at this. And data equals, okay. And you'll just follow, if you'll bear with me for one more moment and create another new variable, this one called Variofit, which equals fit.variogram. So another function out of Gstat, and specify that this uses the variogram called Vario. And I'm going to use an exponential model and specify some starting parameters, but we are now going to estimate what those final parameters end up as. So once again, I'm using VGN to specify a variogram model. Specify a starting range of 900 and a kernel of, or a nugget of 1. Okay. So, yeah, before I plot anything, then I just want to show the parameters of that fitted variogram. Okay. So again, it's a little jargony, but we've talked about the nugget value, and here it's been estimated to be 0.06. We talked about the range parameter, and here the estimate that comes out of our software is that the range parameter ought to be 340 meters. And I'm not really going to talk about the partial sill. It's not super important. But again, this is just displaying estimates of some of the parameters that we've talked about, saying that after 340 meters, the data observations are becoming much less similar. And then the nugget here is saying that at a individual location, if you measured multiple times, you would still have a variability of a variance of like 0.06. Okay, but more intriguing than that, because those are sort of abstract, is to just plot the dang thing and see in a more intuitive way what we're working with. Okay, so this looks something like what I showed you before. We have a curve that is quite similar to the model that I showed you, and that is our estimated model of covariance, or our estimated semivariance. But then we also have the empirical semivariances that are actually used to fit that variogram model. And that's the dots here. And so those dots are actually what people refer to when they refer to a variogram. And the whole point of this exercise was just to show that when we are estimating a variogram model, which is a necessary part of Kriegging, again, apologies for the jargon, the point of that is to use these dots to estimate this curve. And now we have the curve, and we're going to use that curve to generate predictions from our data. And again, this curve is saying how quickly and how much do data become less related to each other as the distance between them grows. So in an intuitive way, this is just capturing that model that the further apart your observations are, the less alike they are. This is just putting it into a very specific mathematical form, but the main thing to know is just the intuition, and also to know that all of the functions I'm using to do that analysis are contained in the gstat package. So if you need to do any Kriegging or any spatial prediction, the gstat package is really useful for that. Okay, so for the Mizdata, we have a grid of prediction locations. It's called ms.grid. And again, for the same reason, I've put it on our GitHub repository, and it has a terrible long URL, but it saves you having to download or struggle with paths. So I'm just going to copy paste that command from the reader and ask you to do the same, and then convert those points to simple features. So okay, coordinates here equals, again, xy. Okay. So I've just imported a grid of points that cover, okay, so what I've imported is a grid of points that cover this entire area, because these observations are kind of sparse, but the grid of points covers everything. And we're going to predict values to fill in all of the gaps in the data. And I've converted them to simple features so that they can work with gstat. Okay, so we have now to actually fit the do the Kriegging. We've estimated the correlation structure with the variogram, and now we feed that into the Kriegging. So in particular, the thing we estimated here is Variofit, so that's going to come back. Again, I use the Krieg command. I'm going to look at this relationship of log of zinc as a function of square root of distance from the river. The data to fit from are just called ms. The data to predict at are ms.grid. That's the grid of prediction points. Oh yes, and I say that the model is this fitted one, it's vario_fit. Okay, Kriegging is very fast. It's one of the nice things about it. Now I want to just plot the predictions on the grid. So we've seen something similar to this before. ggplot of _fit. Okay, so the aesthetic is color equals var1.pred. So the predictions, var1.predictions are predicted. Okay, And then I want a color gradient that goes from gray where pollution is low to red where pollution is high. So scale color gradient low equals, say gray 0.7 equals red. Oh, and I like the black and white theme because it. Great. Okay, so our predictions out of this model are showing greater predictions all along the edge of the predicted area, the prediction area, and that's because that is the Miz River itself. And we saw from the data that the zinc concentration is highest in those observations that were taken adjacent to or in the river. So we are capturing that relationship. We get the greatest concentrations of zinc are predicted to be at locations near the river. And then that fades to gray here as you get farther from the river. So this sort of central open area, it's like a lot of gray, that is less zinc deposits, less heavy metal pollution. That's a good sanity check to show that the Kriegging predictor, the Kriegging estimator, the predictions we get out of it conform with the expectations we had, which would be that the pollution is greatest at the river and gets less as you go farther away. Okay, and we can also plot the uncertainty of the Kriegging estimator. So that is basically just copying the previous command, except that the color now will be by the var1.var, which is the variance of our predictions. And I want to show the uncertainty of the Kriegging estimator because it displays a really important trait, which is that uncertainty is low when you're very close to an existing observation, and that uncertainty becomes greater when you are far away from any existing observation. And intuitively, that should make sense because the more close you are to actual data, the more accurate your predictions ought to be. Whereas when you move to an area where there is little or no data, you'd have quite a lot of uncertainty about what might be happening there. Okay, so again, we start this exactly the same way. It's another simple features geometry. Except this time the color will be given by var1.var, I believe. But I'm going to use the same color gradient, so scale color gradient. Low is gray. High uncertainty is red. Okay, but I also now wanted to draw the observation locations. Okay. And the reason I want to draw the actual locations of observed data is because I want to compare the locations where data was observed to the residual amount or the amount of uncertainty in our predictions. Okay, and I'm again going to add on the black and white theme because it's less distracting. Okay, so these dots, okay, the colors, excuse me, the shading are is the variance of the prediction. So it is the uncertainty in the prediction. And you can see that the greatest amount of red appears where we happen to have no dots nearby. There's some bulges of red. And the reason for that is the dots are the locations where data was observed. So there is low uncertainty close to each of these and high uncertainty when you're far away from all of them. Again, intuitively, I hope that makes sense. It's just a factor of prediction is easier when you know the measured value right next to you than when you're a mile away from any measurement and you're doing something more like blind guessing. Okay, so that concludes what I'm going to talk about geostatistical data. It's a big chunk. It's probably a little exhausting. We can answer some questions before we move on to chapter 4 about aerial data.
Yeah, we've got a couple of questions in the chat. The first one is asking if, sorry, my chat just jumped, lost my spot. So could you go over the Kriegging inputs again and show what each piece of that piece of code means?
Okay, so I'll do that, but I'm not really expecting folks to like, I don't know, I'm not trying to teach Kriegging exactly, but show that this is like Kriegging is a really fundamental, method of analysis for spatial data. I'm trying to give you an example of just an example and also point you to the fact that this is out of the gstat package and the functions to do everything are there. There's a help file there. You can get a lot of help with that package. But again, I will look at this command in a little more depth so that people can hopefully get a sense of what this is.
Actually, Wes, so that was my question. And so I was hoping you could, right when you started, you said something very helpful, but I didn't write it down fast enough. You said, we're going to feed the something points into the model, and then we're going to, so if you could just like on those big general terms, not even necessarily like, yeah.
Right, okay. So I've highlighted here the like what you might think of as a model. If you're familiar with R, if you've done things like, use things like LM, you set up a model where you have some variable to predict on the left and some variables on the right that are of the tilde that are going to be used to predict that. So this is going to say that the log of the zinc concentration is a function of the square root of the distance from the river. Okay, so that's the most familiar part probably. Then we specify that, okay, we have this data called nodes. This is a data frame with a simple features data frame. So it contains spatial point locations as well as the heavy metal pollution that was measured at those points. This is the data that is being used to make predictions. So this is the observed data. It is the green circles in this figure, this bubble plot. Ms.grid is it's nothing but locations. It's a grid of locations where we want to make predictions. So you can look, I can just say plot ms.grid. Oh shit. Well, I'm gonna have to restart R. But don't worry too much. The fact that we were at the end of a chapter is going to make it a little easier. I don't have to actually get caught up. What does it say? Okay. Great. And then was that the part you didn't understand, or were you talking about the variogram model that was being used to model, used as a model of the residual variation?
Oh no, this is helpful. If like the first part was the model, the second statement there, Muse, is the data that you're putting in, and then if you could go through the next two terms one more time, okay. Then that it's starting to make sense. Then the grid that we made is that grid of points. Those are the random points that we put in. And then the model is the one that we built in that previous step.
Right, exactly.
Okay.
The model is the variogram estimate. So model is this curved line, and it's saying, so the big difference between Kriegging and using LM, like this all could be pretty familiar to somebody who's used LM to set up, okay, here's the linear model. here's my data. And then this isn't exactly how you use LM, but you can specify, okay, I want to then do prediction for this new data. That's totally fine. You know, the only thing that's different from what you might do with a linear model is we now, instead of saying that our observations are independent, because they're not, we are saying that the variability in our observations is related according to this model. And what that means is this curved line. So saying that if our observations are 500 meters apart, then their covariance, or sorry, the semivariance of those ones would be about 0.18. So you calculate all of those pairwise distances, you generate a matrix of them that goes into the multivariate normal distribution. All that's happening behind the scenes. The point is just to say that the intuition that the closer together observations are more different than far apart observations is handled by this model of the covariance, which is this exponential curve. And yeah, like that's really the only difference between a Kriegging model and a standard linear model, is that we have this relationship in the background for how closely or distantly related the error terms should be. Is that okay?
Yep, that's great. Thank you.
Okay.
And we have one more quick question, hopefully. This one is about in the ggplot code. Can you explain, so you specified your colors in 2 different ways. For the gray, there's a number that's involved in that. And then for red, you just used a string. Can you just quickly explain the difference in how you're calling those colors?
Yeah, so right, I think the easiest way is just to show you. Right. I'm not sure if I actually did that yet. Okay, so we have this figure here. The gray 0. Okay, so sorry, I'll start with the easy one. Red, this is how you typically specify a color in R, at least if it's one of the built-in colors, is you just call it by its name, which is a string. So that might be pretty familiar. Now gray, like you can do grayscale stuff, and that's where this function comes from. If you scale this number in here between 0 and 1, you get colors. At 0, this is closer to white. At 1, this is closer to black. And the reason I specified it this way is because when I first made this plot, I didn't have that black and white theme. And you can see the background has a gray and the data has a gray. And if I just set that as gray, whoops, I think they come out as the same color. Well, not quite the same color, but really similar. So it's hard to tell the difference. So in order to do that, I just changed the gray here. So it's still gray, it's just a different gray. Makes it a little easier to see, made it a little darker. But then I realized that I could be done with all that and just do the theme PW. And then it's totally clear how the background is different from the data because the background becomes white. So yeah, anyway, that should answer that question. And I'll tell you what, I'm going to skip over the section on aerial data, not because it's not important, but because aerial data works really similarly to geostatistical data with some exceptions. And also that I feel like my treatment of aerial data was a little bit undercooked. So I don't, like if I'm going to skip one section of my talk, I'd prefer it to be this one. The code is there in the workshop reader. So those of you who have a particular yen to work with aerial data should find it there. But I do want to say, before I move on, that this was going to be one of my goals for you, finding the R packages that are best for analyzing a particular kind of data. And with aerial data, that is SPDEP. SPDEP has the best functions for modeling and working with and interpreting data that is displayed in a aerial format. So meaning like, in this case, it's an example of the rate of sudden infant death in each county of North Carolina from 1979. So the upshot of all of this was to show that it looks like there might be a spatial pattern to the that rate, but it's not. There's not strong evidence that there's any spatial like trend, that it could just be completely random noise. But anyway, that code is all there in the reader, and I would encourage those of you who are particularly interested in aerial data to go back and work from there. But for myself, I'm going to jump ahead to chapter 5, which is point processes. And to begin with my goal of telling you about what are the packages you want to use. Point patterns are the worst of the, in terms of there being no consistent or good packages that work well with like SF and have all of the features and using a standardized vocabulary. Gstat is really good for geostatistical data. SPDEP is quite good for aerial data. SPATstat is the best we have for point pattern data, and it's not that great. But you can do everything. There are a lot more stumbling blocks because there's frequent needs to convert data from one format to another. I'm really sorry about that, but if you're working on point patterns in R, you have to be prepared to do a fair bit of pretty technical programming. But I've taken care of that for you today. I've prepared a really simple example that I think I've worked out any kinks, so we're not going to have problems. And with that, let's begin. If you're following along, you probably do not have the SPATstat package. You might not have the Tigris package. So please install those via install.packages stat, for instance. I already had it installed, so I didn't have to add anything. Similar with Tigris. We already did SF, and if you have the tidyverse, you have these three already. So I'm just going to load these packages. Okay. So to introduce you to point patterns, the data set that I'm going to use is something I downloaded from iNaturalist, which is a really cool resource where people upload the pictures of life they find out in the wild, and people identify it for them. And the data that I downloaded were locations of Valley Oak in Sacramento County. So first thing to do is to import that data and the Sac County shapefile. And once again, because I have put the data onto the GitHub repository, which involves a nasty URL, I would advise copying and pasting that import command from the reader directly. Okay, and then I want to convert that to a simple features object. So I need to specify that the coordinates came in as longitude and latitude. Okay, and therefore I want to specify a projection. So I'm going to say CRS equals, okay, so the projection it actually uses right now is EPSG 4326. So that's your basic Latin long. And rather than use that lat and long, I want to actually do a projection. So I'm going to say oak equals, and I'm going to transform that to a projected data set. And I'm going to use the California Albers projection, which the EPSG code is 6414. So I think that a lot of you are familiar with the stuff I'm talking about now, because I think that's more the typical map time content.
It's also what we covered last week. So
Excellent. Okay.
Yeah.
Okay. So we have loaded and transformed the data, or loaded and projected the data. Now I'm going to get the Sac County shape file. So this is from the Tigris package, which links directly to the census. So I can just get all of the US counties. Then I can say that Sac County is the county where the county name is Sacramento. And finally, I want to project the Sac County shape to the same projection as I used for the locations of the oak trees, the valley oaks. So I'm going to say Sac County equals so just using the same EPSG code, 6414, California Albers. Okay, so great. We get our first payoff. We can now plot the data. So I'm going to use ggplot again. And I'm going to use a simple features geometry. Then add to that another simple features geometry with the oaks. And add the black and white theme. Okay, so that's Sacramento County with all of the observed locations of Valley Oaks. Pretty cool. The eye should be immediately drawn to one very salient feature, which is that the Valley Oaks are very much clustered around the American River. Okay, so when we are talking about analyzing point data, generally the first question the first thing our mind jumps to is the data following, or are the points following a Poisson distribution, like a simple homogeneous Poisson distribution? Because if they are, then one, analysis is extremely simple, and two, there's not much more you can say. Like the feature of the Poisson distribution is that if you were to draw a square anywhere in the domain, you would expect the expected number of points within that square would follow a Poisson distribution, and that the intensity of that distribution, or the count, would depend only on the size of the square. And that's talking about expectation. Obviously, not every square would have exactly the same number, but the point is that if the data, like if these trees were following a Poisson distribution, you could draw a square anywhere in Sacramento County and expect to have the same number of Valley Oaks in it. Now, looking at the actual locations of the Valley Oaks, we see that that's probably not true, because if your square covers part of the American River, you're going to have a decent number of Valley Oaks. And if your square is drawn like sort of in the southeast of the county, you are going to be quite unlikely to have any Valley Oaks inside. So the eye test is telling us that these points are not following a completely random distribution, or a Poisson distribution. And the actual analysis, the simple analysis I'm going to show you, is going to back that up. We're going to reach the same conclusion, but I want to explain to you before I get started exactly what it is I'm doing and why. And that will hopefully help you as we go on. Okay. Okay, so in order to analyze this data as a point pattern, we first have to convert it into an object of the PPP type, which the PPP stands for Poisson point process. And that is part of the SpatStat package. So that's why we need the SpatStat package to be installed. So we get the coordinates. And then turn those into the PPP object. So we specify, we just have to specify the coordinates of each point. So this is kind of ugly. This is where if the SpatStat package were well integrated with SF, you wouldn't have to do this. You would just say that treat these points as a point process, and the software would handle the rest in the background. But alas, all right. So we have to specify the window. That's being the domain of the point process. And that for us is Sacramento County. So fortunately, this is one nice integration that I can say the Sac County shapefile should be treated as a window. Oak Loke not found. Because that should be Oak Lokes. Okay, warning message, there's duplicated points, that's fine. There's just multiple trees at the same point. It could be two branches growing out of the same, two roots growing, two trunks growing out of the same roots, or a repeat observation, I'm not quite sure, but we will let it be. Okay, so I'm going to plot the point pattern, although it won't show us anything particularly new. It's just that now that we've converted to the SpatStat object, we get this. Yeah, this is what we have. I mean, it's uglier, but it at least is the same thing. Okay, now I want to check, do the data follow a Poisson distribution? And the way we do that is using using Ripley's K function. And the way Ripley's K function works is by calculating for each point observation, if you draw a circle of increasing radius around that point, how many points should be within that radius if the data are actually from a Poisson point process. Now, the thing about that is you can actually draw circles of increasing radius around each point observation and count the number of other points that lie within that radius in reality. So you have a theoretical number, which is how many you would expect to lie within each radius if you have a Poisson distribution. And you have a reality, which is how many points actually do fall within that circle of increasing radius. And so the point of Ripley's K function is to compare this theoretical number to this actual number, and thereby be able to say, like, does this actual number bear any resemblance to this theoretical number? And remember that for our data, when we look at it, the eye test tells us that no, this data is not following a Poisson distribution, that there is in fact clustering of the points. And therefore we should not see our data follow the theoretical K function, but we have to actually do the test ourselves. So plot. So to calculate Ripley's K function is a function within SpatStat called Kest, K-E-S-T. And it only takes one parameter. which is the PPP object, the Poisson point process object. And I just want to plot the result as soon as I have it. Okay. So with the increased font size, this plot came out a little ugly, but I will tell you that the black line represents our data, the actual observed pattern of how many points are contained as the radius of a circle grows around any particular point. The blue is the theoretical number. That's if the points are actually following a Poisson pattern, then you would expect the black line and the blue line to be very similar. That's clearly not the case. The black line is clearly above the blue line, and it is above that blue line across the entire range. Therefore, this is not only saying that our data do not follow a Poisson distribution, but it is showing evidence of scaling across, evidence of clustering across the entire spatial scale of the data. So this Ripley's K function is really suggestive of points that are clustered. And of course that accords with our eyeball test. Okay, so to really get more like realistic or more, how to put it, more rigorous about this test, it's not enough to just do a single theoretical K function. You would want to do multiple repeats of that where you sample different random points. However, running that takes a bit of time, and I'd rather skip it for now, but it is contained in the reader. Anyway, the last thing I'm going to do before we go is to just get a first pass at what is the density of the oak points, because we saw that it is not uniform. There should be some pattern to the density of oak trees. And again, the SpatStat package provides a pretty handy function for estimating that density. It is just called density of oak points. Okay, so you don't want to trust this plot. Like, this is not the end of the process, but it is extremely simple. And I'm just trying to be simple today, do some introductions. Here is our first pass, simplest estimate of what is the actual density of valley oaks at locations in Sacramento County. We can see that the highest intensity is roughly where the American River is located. And then there's this, another warm spot, sort of, that might be the San Joaquin River. I'm not exactly sure what happens at the very southwest end of Sacramento County. But anyway, that accords more or less with the data that we were working from. We have, so big cluster at the American River, and then a smaller cluster down here in the south central part of the county. Okay, so that's it. That's all I want to talk about today. That's all the time that we have. But I don't know, I'll take questions now. We'll get through as many as we can. And I don't know, fire away.
Okay, thanks, Wes, for this workshop. In terms of timing, I'm going to go ahead and stop the recording now and just thank you very much. And we can hang on the call for a little bit and answer some more questions as we go. But big thank you for you doing this. It's a workshop we've needed for a really long time, and I learned a lot. So I hope the rest of our participants did too. All right, thanks, guys. Hang on the call and we'll chat a bit after this.
Thank you.